Hello and welcome back to CS210. This is our first video for part 2. We will discuss about Cuckoo hashing. Okay, so let's recall one particular linear data structure from Module 3 called hash tables. Well, this is relatively fresh because this is one of the questions from our first exam. So for hash tables, our goal is to provide a mapping through the hash function such that accessing and storing elements is fast. The running time is the running time of your evaluation of the hash function. However, there's a constraint. The size of the hash table is much less than the possible keys that we have. And by pigeonhole principle, or equivalently, since the cardinality of all possible keys is much greater than m-1, there is a possibility of collision, which means at least two unique keys from this set can hash to a single location in the hash table. And so, hash tables in general have to deal with so-called collision resolution. So we discussed several ways how to deal with it. The first one is not to limit the space to M, but allow an external data structure to hold the data. One example is by chaining, so using a linked list to store all the data hashed to a particular location into parang just one linked list. An improvement of this auxiliary data structure is by using binary search trees, because when we have chaining, if we look for a particular element, we have a running time of checking all the elements that are hashed into the same location linearly by checking each item one by one. However, for binary search tree implementation, log of total number of elements hashed to a single position lang. And then the second approach is called open addressing, where we allow the elements to utilize some unused positions in the hash table by manner of linear probing. Okay, so the third method, which we did not discuss the last time, is perfect hashing. So for perfect hashing, we need to have a clever way of hashing the elements so that we can totally eliminate yung collision. So, one solution with the perfect hashing is called the Cuckoo hashing. This solution is published in 2004 in the Journal of Algorithms. This paper is from Pag and Rodler. So in Cuckoo hashing, suppose we have the same assumption. We have m slots and we have a relatively large set of keys to be hashed. Here we have two hash functions na. So instead of just using one, we have h sub 1 and h sub 2. We can assume that these hash functions are truly random or to no relationship at all, except we have the condition. The condition that the evaluation of the hash function using the first is not equivalent to the evaluation of the second hash function, and that is true for any key x. So given this condition, any item x or any key must either in the evaluation of the first hash function or in the second hash function. And if we assume this, looking up or searching for a particular element x in our hash table takes exactly two comparisons lang or in constant time. And for deletion, since deletion involves searching, then deleting, deletion of a key will also need exactly two comparisons or the same, constant time lang din. But if we wanted to insert an element sa hash table natin using Cuckoo hashing, the idea is to first use our first hash function na h sub 1. For our key x. And if may laman na yung slot na yon, what we need to do is to kick out that element na nandun sa mismo location na yon and try to place it in another location so that it can belong either to this evaluation of the first hash function or the second hash function. So, sometimes yung location ni h sub 1 and h sub 2 may laman na, so we need to repeat this process until all elements stabilize. Okay, so sometimes it is also possible that inserting a particular element will form an infinite cycle. So, hindi na siya titigil dahil lagi tayong nagpapaalis ng currently naka-reside na dun sa slot na yon. And if that's the case, masasabi natin na the insertion fail for those two hash functions that we have. And in the event that it happens, what we need to do is to perform a rehash. And by rehash, we need to choose another h sub 1 and h sub 2 and insert all the elements back into the table. Okay, so it's also possible that we need multiple rehashes or multiple values of h sub 1 and h sub 2 such that we can arrive at a stable inserted elements na wala na tayong masyadong tatanggalin or papaalisin. Okay? Okay, so let's try to visualize the advantage of using two hash functions. So let's try to create a graphical representation where we have some x-axis, tapos we have a y-axis. So okay lang yan, dito tayo sa positive na quadrant mag-play because we only have positive values for the indices. So let's say index 1 tayo, let's say we have 1 to m, which is the capacity of the hash table. So, idea is, we wanted to try to have a mapping from the set na medyo mas malaki, which is yung possible value for the key. So, meron tayong condition na ganito. N is much greater than m. Yung gagawin natin is, if we have some x here, we wanted to have a function that maps yung x natin to the set of 1 to m. So, for a single hash function, let's say h of 1, suppose meron tayong ganito. And for h of 2, we have another hash function that maps from 1 to m din. Pero we have an additional condition dun sa Cuckoo hashing na dapat yung evaluation ng h of 1 and h of 2 natin for the same x ay not the same. So, pwede tayong gumawa ng ganitong function. And let's try to bound this kasi ito lang yung mag-matter sa atin sa ngayon. Okay? So, imagine that we have some x na ang evaluation ng h of 1 is this particular value. So, we have some I. Okay? And if we use some h sub 2, yung evaluation ng x natin will be some I prime. Okay. So, ang requirement lang is that dapat hindi siya mag-hash to the same position if we use h sub 1 and h sub 2. So, ito yung condition na yun. Okay. So, bakit natin ginagawa ito? Kasi, hindi naman natin alam yung distribution of all the keys na darating at kailangan nating ilagay doon sa hash table. So, sometimes, uniform yung distribution ng keys. So, lahat yan ay pantay-pantay ng probability na malagyan ng laman. So, if that's the case, then we can utilize this part of the function para we can cover the lower part of the hash table. And then we can utilize this for the second half of the table. However, if we have the set of keys na highly distributed sa area lang na to, we can also use this corresponding pair of hash functions so that we can distribute yung mga elements na nandito to several location of the hash table na hindi lang siya highly distributed lang din sa isang portion. So, for example, I can utilize this for some values, and then I can also utilize the other half using yung hash function 2 so that I can utilize this part. So in this case, hindi ko kailangang maglipat-lipat because anticipated ko na whenever nagkakaroon ng high density sa area na to, I can cover the two location of the hash tables nang hindi ako masyadong maglilipat or wala akong underutilized. Ganun din yung case if we have a lot of keys coming in from this portion of the domain. So, if that's the case, then I can allocate yung some of the elements dito sa space na to and some elements sa space na to. Our next question is, how efficient is Goku hashing? So yung lookup and deletion is simple, and we only need a constant time to search for a location and to delete a particular element. But for insertion, medyo mas tricky because there's always a possibility of displacements and rehashing because of our strict condition na dapat nasa dalawang possible location lang yung key X if we have the two hash functions. So, in practice, we usually perform theoretical analysis first before we try to get to an empirical result. But it never hurts if we get some empirical performance data first. So here's the result of the empirical testing. Here we have our x-axis as the total number of insertions. And then we also count the total number of displacements or yung pagpapalayas ng something kapag meron ng content dun sa isang location na yon. So, when we try to plot it using some actual data set and by counting the total number of insertions and total number of displacements, surprisingly, we obtained a linear result. So, if we have n number of insertions, we have a total of n displacements then. Okay, so, ano kaya yung makukuha natin from that? Empirically, ang nangyayari ay when we insert one element, we displace only one. So, ang goal natin is when we insert an element, ang expected running time is also constant time. Okay, so ang gagawin natin, the next step is to know for which conditions ganito. Because for this empirical result, there's a condition na relating the total number of elements to be hashed and available space sa hash table natin. If you try to manipulate this is just m is greater than 2n. So, mas malaki yung capacity natin or yung space for the hash table compared to the total number of elements to be hashed. So, sa anong cases okay gamitin si Cuckoo hashing, sa anong cases hindi natin siya gagamitin? Or equivalently, how do we set our m given an expected n? So, let's have another plot showing yung probability na we can claim this with respect to some parameter na tinatawag na load factor. Load factor is alpha. This is equal to n over m. N is the total number of elements. M is the total capacity. So, if n is equal to m, then we expect na lahat ay milalagyan. If m is a very small number compared to n, then ang load factor natin is beyond 1. Ibig sabihin nun, hindi talaga enough yung capacity M. Okay? So, pag kaunti lang yung laman, yung kailangang ilagay, we have a load factor na mababa. If meron tayong alpha na greater than 1/2, marami tayong elements na kailangang ilagay sa M and almost mapupuno natin yung M. So, we try to dissect it into several parts. The first condition is if we have a load factor na mas mababa than 1/2, then ang sabi dito sa graph na to is that the probability that the insertion succeeds, and if we have a load factor greater than 1/2 or medyo malapit na dun sa total capacity ng M, then we have a probability that is closer to 0. So, given that we have this plot, we can always allocate a hash table na ang load factor is always less than 1/2. Okay, so if we expect 10,000 10,000 elements in our hash table, then we need to allocate 20,000, parang ganun, or more.